Welcome back. We're going to be looking at another concept dealing with descriptive statistics today, and that is how dispersed or widespread data is, and how do we begin to quantify that and not just use words like, yeah, it's pretty spread out or not very spread out. There's ways to categorize different data sets by how much, right? We can quantify the amount of dispersion there is within data sets. So let's take a look at that. There's a couple of different ways that we do that. What's going on here? Here we go. Okay, so a couple of things we're going to need to know about when we're looking at dispersion of data is first off, the concept of outliers. These are data points that just don't seem to fit the rest of the group. Now, sometimes we can play that by ear, kind of like how we feel about it. And there's also a numerical test for what technically qualifies to be an outlier, sort of something that just doesn't fit the rest of the data set. There's something called variance, and finally something called standard deviation. You may have heard of standard deviation before without knowing what it actually is. It's one of those sort of fancy math words that people have heard before but don't really know. Okay, let's see here. We're at a veterinarian's office. We're going to be taking a look at the age of the different cats that this vet perhaps has been working on. We're going to find the mean, median, and mode of the data set. That goes back to a previous lesson. And we're going to try and identify if any of the data points kind of distort our calculations of the mean or our observances of the median or anything like that. So let's take a look. We're going to go back, do what we normally do. I'm going to take a look. There's some of the cats are 10, 11, 12, 13, 14, 24, and 25. Well, immediately I see that something a little bit weird about that set. So there's only different seven different ages of cats. So I go ahead and put those ages down in a column on a spreadsheet. I'm going to create a frequency column beside it and indicate how many there are of each of those. That's certainly a huge time saver when we are at the data entry stage. It'll make our lives easier overall. And I go ahead and go back and make a new calculator screen, go to the one variable statistics. Don't forget now you've got a frequency list, so go back and enter in the names of the columns, cats and the frequency, there you go. And then we're going to see our statistical analysis for one variable, or univariate data. And you can see that the average age of the cats was 13.6. There are 15 cats overall. And there's various other things in here that we're going to discover in time. The median age of the cats was 12. Okay. But I think, it doesn't take much of an observation to see that 24 and 25, those are quite different age cats than all the other ones that this person was working with. I'm assuming it's a vet. Anyway, so we're basically asked what would happen if we were to sort of exclude the 24-year-old and the 25-year-old cat from our consideration. How different would the data set appear to be in terms of its mean and median if those calculations did not include those two elderly cats? So what we're going to do is we're going to go back to our table and we're going to remove the 6th and 7th row of data. Basically, the 24-year-old cat, the 25-year-old cat is removed from our consideration before we go ahead and make the calculations. And we have to make the calculations again. And you're going to see, and I put them side by side so we can do a direct contrast with them. The mean age was 13.6, but it's dropped now to 11.9. But it didn't affect the median. Remember, the median is the middle number. And since there was a big cluster of 12-year-old cats in the middle, taking out the two, what I'm going to call outliers at the end, didn't mean that the middle-aged cat is not middle-aged. I mean, the cat whose age is in the middle is any different than it was. So removing outliers can have an effect. It can have an effect on the median, but it's definitely going to have an effect on the mean. And so that's something to consider. I want you to hit pause on the video right now. This is just a chance for you to, work with your GDC and make sure that you're getting some of these concepts right. We're looking for the mean, median, mode of these sets, and then make a judgment call as to if you think any of the data points listed should be what we call an outlier or just non-representative of the group. An extraordinary value, some sort of aberration. Okay, hit pause now and come back after you finish these three little questions. Okay, assume you've done that now. So another way that we can measure how spread out data is, or what we call its dispersion, is one of the ways is the range, and that's the difference in the values from the highest and lowest ones in the data set. But there's also something called standard deviation, which is related to something called the variance of the data. Now there's a very fancy formula. There it is. It comes in two formats. And it's a little bit difficult, but I want you to notice the final line. Oops, sorry, I'm going to go back here. I made a mistake. In examinations, you will only ever use technology. So why is it present here? Some students who choose to do a statistics-based internal assessment, the IA, the project, may end up choosing to calculate the standard deviation. And in those cases, it's expected that you provide to your examiner proof that you are really an expert on this, and so you would be asked to do this by hand in those cases. So let's take a look here. So we've got two different classes who are writing a test. Each test has got a number of students in it. I'm not going to count them up. There's a lot of them. And I went ahead and I figured out the mean for both sets. Now, a casual observation would just say, yeah, there's some high numbers, some low numbers in each set. But there's actually something quite significant happening differently in each of these two classes. There's something about homogeneity or uniformity of the data. And it's hard to observe that just by examining the mean. Now you'll notice in the first case the mean is 10.1 and the second case is 9.5, and those numbers are not dramatically far apart from one another. But if I was to reorganize the test data for each of the two tests or two classes or whatever into a frequency table, it's very easily seen that there's something wildly different about these two data sets. And this doesn't have to do with outliers, it has to do with clustering or dispersion. You can see that in the second case that all of those zeros for frequencies, the scores from 3 to 7 and then again 12 up to 19, there were no cases of those. This class is very homogeneous, meaning very similar to one another in respect of their test scores. 8 through 11 were the only scores, and there were many, many of them. However, on the first test here, there were scores as low as 3 and as high as 19, and most of the numbers in between 3 and 19 were visited by at least one student. So and some of them, like 12, for example, were visited by or were achieved by many students. But I wouldn't necessarily say anything there is an outlier. So there was just a separate way that we got to think about dispersion. What we're going to do here is we're going to take a look, and I entered all the data for that first test into a spreadsheet, and then I did it again for the next one. And you can see that there's the mean, 10.1 and 9.5. But here's the next thing you're going to take a look at, and it's right here where I'm holding my cursor, right there. And this is known as the standard deviation. The standard deviation is a gauge number. It's a very fancy formula that you saw on a previous slide that tells us how spread out the data is. It's measured in the same units of whatever, so this would be 3.65 test points. And over here is 1.13. And now I'm sure you can remember just a slide ago when we saw all that data, the second test only had scores of 8, 9, 10, and 11. So those were very closely clustered. Hence, the standard deviation score is much lower. It's less than a third of this one. Now, it's a little hard to properly define standard deviation right now, so far as to say this. The bigger the number, the more spread out the data is. The smaller the number, the more clustered they are around the median. All right. So in both cases, you can see there's 48 test scores, and there's the mean, and there's what we call the standard deviation. And it's that little symbol that you see in the front here. It's called that's the lowercase value of sigma, like lowercase letter for sigma. It looks like a circle with a little, like a hat, like the bill of a hat or something like that, or a really cool haircut. So here we go. You'll notice that if you could theoretically, what we do here, you take the scores. I'm going to do it for the smaller one. 8, 9, 10, 11. Here's the frequency. You take the difference between the mark that each one there was and the mean. In the first case, the mean was 9.48. And so I'm going to subtract this number here by 9.48, get these numbers. You square all of these numbers and then multiply by the frequency, and you get this number here. And then that number is divided by 48, which is the number of numbers in the set, which you get this number here, 1.291, whose square root is the standard deviation, and there it is in this green box right here. Do you need to know that? Not unless you're going to do a stats-based project for your internal assessment later in the course. All you need to know is that this symbol here is it, and that's where you find it. Okay. And that is that formula here would have yielded this the exact same thing. If you're ever asked for the variance, this is kind of old-fashioned here. It's just the square of the standard deviation. Basically, the number before you would have taken the square root, 1.291. All right, so let's see what else we're going to do here. The last way that we have at this stage of the course for measuring the dispersion of data or how spread out it is called percentiles. And what we do is they think of the data as being arranged in order, and we assign a percentage scale to how far. Like you start at the 0%, the lowest score is the 0 score, and then the highest one is 100% of the way through the data. So when you get to the second half, end of the second half, 50%, you're halfway through the data. Now, we also tend to break up the top half and the bottom half into their own halves, if you get my meaning. So basically a quarter of the way through, or what we call the 25th percentile or lower quartile, the lower quarter. The second quarter, Q2, is the median because you're halfway through now. And then the third quarter of the data, the boundary there is called the 75th percentile, and we call it the upper quartile. So sometimes but those aren't the only percentiles. You can go any percent you want. For example, you could be at the 85th percent score, meaning you're 85% away from the bottom or 15% from the top. And the calculator is going to do that for us too. Now, since the quartiles divide the data into quarters, the lower quartile is the measure of where the first 25% is, and the upper quartile is the boundary for where the final quarter begins. So in between those two must reside 50% of the data. If you think about it, if you take off the top quarter and take off the bottom quarter, you got half the data left in the middle. In fact, you've got the middle 50%, and we call that the interquartile range. And it's simply the difference between those two numbers. You actually take the one number, which is the upper quartile, and subtract the lower quartile to get a new number, and that is the range of points or whatever your table is measuring in which 50% of the data resides. So if I was to take a look at that last one that we had with the test scores of 9.47 with a mean, notice down here in this section here, also on the single variable or univariate data, it'll say Q1 is 8, and that's the 25th percentile, and Q3 is 10.5. So if you were to want to find the interquartile range, you'd simply take 10.5 minus 8, which is 1.5. So that means there was a spread of 1.5 marks on this test where the middle 50% of the data set resided. So the middle 50% of the students, not the top quarter, not the bottom quarter, they were all within a 1.5 of each other on the test. Now, I think it's interesting to note that at the very end of our summary list here, our single variable stats list, is this number 61.972, which we got over here. And so that whole big calculation that I was describing earlier is also right here. So if you were to take this number 61.9792, divide it by 48, do a sum on that, take its square root, you would get 1.3632. So a bit of redundancy in there, but sometimes it's handy to have access to all those things. Okay, during the middle of this video, you were asked to hit pause and work on exercise 3C. I am going to ask you to hand that in. And there's more here now from 3D, and you can put those together. And if I take a look at them, lots of questions here: standard deviation, interquartile range, etc., and we're in this section here, 3D. It's questions 2, 3, 4, 5, and 6. I'm here to help you. That's it for now. Okay, let's everyone get to work, and good luck.